Okay, momentum is conserved. Momentum is always conserved. That's one of the universal laws of physics. You can always assume it's true. Momentum is always conserved. But according to Einstein's first postulate, the laws of physics must be true in all frames of reference. Momentum has to be conserved. But with relativistic effects, our description of momentum must be modified to account for relativistic effects. So the fact that we have length contraction, the fact that we have time dilation, we have to now modify our original understanding of momentum. So momentum, before we understood it to be P is equal to mv, right? That's our definition before. But now that we are talking about something moving near the speed of light, we have to throw a gamma in there. We have to adjust. Okay, so now we're going to get P equals gamma times mv. And remember that this relationship is going to reduce to P equals mv when v becomes really small. So if v is small, then this goes to 0, this becomes 1, square root of 1, and you get the original. Okay, so it reduces to what we understood to be the rule for momentum before. So just to kind of keep in mind, T equals gamma T sub 0, L equals L sub 0 over gamma, and then P is equal to gamma times n. So remember how we talked about time dilates, right? Time dilates, time gets bigger, mass increases. So mass increases kind of the way time does. So the faster you go, the more massive something becomes. When P, so it's going to reduce to P equals mv when v is much less than c. And that's been true for all these formulas. Note at higher velocities, it's as if the mass, or better put, the inertia, increases. So take a look at this. Remember, work is equal to delta KE. If you apply massive amounts of work to get a particle moving to near the speed of light, what happens? Right? So this would be what you would expect. This would be the curve for applying force over distance, you get an increase in energy. But this is what has to actually happen, because this represents the speed of light. The more force, the more energy, the more work you do, you cannot get it to go any faster. All you can get it to do is to get more momentum. So you can't exceed the speed limit. Okay, so we're going to reduce the kinetic energy to look like this. So we talked about the momentum equation, and now here's the energy equation. Kinetic energy is now going to be mc squared over this gamma, gamma times mc squared, minus mc squared. Note that the velocity is equal to 0, the kinetic energy is 0. So that reduces to the 1/2 mv squared eventually. Okay. In order to reduce it, you'd have to do this binomial expansion, which we're not going to do, but it does reduce. All right, keep going. What does this look like? So that is just another way of saying kinetic energy is gamma mc squared minus mc squared. Does this look similar to something that Einstein might have said? We're getting there. We're getting to Einstein's equation for energy. And here it is. Kinetic energy is gamma mc squared minus mc squared. Again, this just came from, we have to adjust the equation for kinetic energy at relativistic speeds. So we adjust it, and then we rearrange it. And we say, let's put the gamma over here. Gamma mc squared equals mc squared plus kinetic energy. Or the total energy of a system is equal to gamma mc squared, which is mc squared plus the kinetic energy. Now, up till now, we've only talked about the total energy being kinetic energy, or kinetic energy and potential energy, and kinetic energy and thermal energy. Okay, so these are different kinds of energies. But now what we're saying is the total energy of a mass, okay, or a system of particles, is its kinetic energy plus mc squared. So that's a new term in there. That is Einstein's famous energy equation. And what this is the energy associated with mass just for being. That mass itself has energy associated with it. So we've talked before about conservation of mass. We have conservation of mass. Whatever mass you lose here, you're going to gain over here. And then we had conservation of energy. Total energy is potential plus kinetic, and then we have problems with bullets that run into things and they heat things up, and you can use conservation of energy. Okay, so now we're taking it a step further and saying we don't really have a conservation of mass and a conservation of energy. They're not separate. They're actually together. It's the conservation of mass and energy that you have to keep the two together when you start talking about things that are moving at really high velocities. So we say it's the conservation of mass and energy together. What that means is, if you have a quantity of mass, if you could separate out, you can have less mass and energy. Like you could break a big mass into a smaller mass plus energy. Or you could take a small mass and add energy and get a bigger mass. That's the idea behind this premise. Okay, so take a big mass, break off some energy, and you'll get a littler mass. Anybody think of an example where we do that? Yeah?
Radioactive decay.
Yeah?
Nuclear bombs.
Nuclear bombs. That's what they're doing. The whole point of a nuclear bomb or a nuclear reactor is to take nuclear mass energy and convert it to a smaller mass and give off energy. So little mass plus energy will give you a bigger mass. Okay. Einstein's energy equation, mass has energy associated with it. If we could just harness it, you could convert one. So here's an example, right? E equals mc squared. So take the mass of an electron, 9 times 10 to the minus 31st kilograms, times 3 times 10 to the 8th squared is going to give you 8 times 10 to the minus 14 joules, or 0.51 mega electron volts. That's a pretty good chunk of energy for one electron. So if you can convert more than one electron, you start getting really substantial amounts of energy. The sun in 1 second, 4.5 billion tons of rest mass are converted to radiant energy in the sun. That's what we're seeing. That the sun is an E equals mc squared equation. It's converting mass into energy. The good news is there's enough mass to last a lifetime, or many, 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 many lifetimes of ours. Okay, so the energy association led to the science behind the atomic bomb. So here's an example problem. Let's try this one. Find the energy of gamma radiation resulting from the annihilation of 500 protons and 500 antiprotons that are moving slowly before they collide. Okay, what does that mean? So we haven't talked about particles yet, but we have particles and then we have antiparticles. Antiparticles have such a short decay rate that they don't last very long. So protons are stable, antiprotons aren't stable. But if you have a proton and you have an antiproton, whenever they meet, they collide and they annihilate each other and they disappear into pure energy. Okay, so that's just the behavior we'll talk about when we get into particle physics. So you have 500 protons and 500 antiprotons. If you have a proton and antiproton, you can assume that they have the exact same mass. Okay, so proton, antiproton, they collide and poof, they give off energy. The energy they give off is in the form of gamma radiation. Yes?
Does that not violate the conservation of mass?
Because you have two masses, and then the masses are going to disappear and convert entirely into energy. So it's a mass plus energy, mass plus energy. The total of what you had before equals what you have after. It's just that the mass is all converted into energy. So that's the question here is how do you calculate that? So you'd say, well, energy equals mc squared. So what's the total energy? Well, what's the mass of the proton? I don't know. What is the mass of a proton? Formula sheet?
Mass proton, 1.672 times 10 to the negative 27.
1.672 times 10 to the what?
10 to the negative 27 kilograms.
Okay. So that's the mass of one proton, but we have a proton and an antiproton, right? And they're going to collide. And we have 500 of them. So we basically have 1,000. 500 of each. So we have 1,000 of these particles, 3 times 10 to the 8th meters per second quantity squared, and that's going to give us the energy value, okay, of these protons. It's only 500. That's not very much, right? It seems like a lot. And that's going to give you 1.5 times 10 to the minus 7 joules. And it says assume they're moving slowly before they collide, so it means assume they don't have kinetic energy associated with them. It's just their rest energy. Okay, so you'll do little problems like that. Albert Einstein was very conflicted on his role in atomic warfare. I made one great mistake in my life when I signed a letter to President Roosevelt recommending that atom bombs be made. But there was some justification, the danger that the Germans would make them. Yeah, you can see that would be kind of a conflicting place to be. You know, should we build these? No, we shouldn't build those. These are terrible devices. But if they build them first, then we're not going to have a say in the matter. And it's really interesting as you look at historically kind of what happened in terms of the use of nuclear weapons. And a lot of testing and a lot of fear and a lot of deterrence because we've developed more and more powerful nuclear weapons. But what if they were in the hands of an evil dictator? Or if they get in the hands of terrorists? You know, so they're still out there and frightening to think about. We have successfully harnessed nuclear energy to provide us energy and power, but with, you know, Chernobyl and more recently Fukushima and you know, 3 Mile Island that was when I was in high school, where there was a containment breach and none of the radioactive material actually escaped, but it was scary enough that it just completely shut down the nuclear development program in the United States. And Japan has shut down all its nuclear power as well because of the accident. So it's fraught with peril, but we need the energy, and it at least doesn't give us the greenhouse gases. Okay, so a couple concept questions. As the speed of a particle increases toward the speed of light, the force needed to give it a fixed acceleration will... Okay, think about this one a little bit. As the speed of a particle increases toward the speed of light, the force needed to give it a fixed acceleration will... Some people are voting. They get it right away. What do you think, Jasmine?
I don't know, I just guessed decrease.
The force needed to get it to accelerate is going to decrease. No. The faster you go, the more massive you get. The more massive you get, remember F equals ma, right? So if you go faster and faster and faster, your mass is going to get bigger and bigger and bigger. So to get the same acceleration, remember what acceleration is? Force divided by mass. So if your mass gets bigger, then your acceleration also has to get bigger. When we get to the very end of the year, we'll talk about the I hate it, Large Hadron Collider. I really hate losing words. And how they take protons and they just make them go faster and faster and faster. And they get them to like 0.99 times the speed of light. And so by the time that they actually collide, they're incredibly massive. And then they just annihilate and create cool new particles that last for just a really, really brief period of time, and they study those. So we'll talk about that in the next couple weeks. Okay, for a chemical reaction that absorbs energy from the surroundings, the mass of the products... Okay, I'm going to let you talk with your neighbors about this one. Try to think about it. Try to think what's going on. So you have a chemical reaction, and you know from chemistry you have like two products, and they're going to react, and it's an endothermic reaction. Okay, so it takes heat in. Does that make sense? You take heat in. You have two reactants. They take heat in, and then you have products over here that are left at the end. The question is the mass of the products more? Now, it's not going to be a lot more. It's going to be very, very, very slightly more or very, very, very slightly less. Is it going to be more, or is it going to be less than it was before the reaction? Okay, so talk it over with neighbors and see what you think. Okay, what do you think, Lucy? Is greater than the mass of the reactants. Why do you think so?
Because if it's taking energy in, then the mass seems to be bigger.
It's taking energy in, and so the summation of that rest energy mass combination has to go up. That's correct. Good. Okay. And then what about this one? Compared to the mass of an unstretched spring, the mass of a stretched spring is... Talk it over with your neighbors.
they're not the same, whatever it is, it's like, because they're together, right? You just think about
Yeah.
Guys, I downloaded 30 out. Last night.
All right, what do you think? What do you think, Soren?
Would it be slightly smaller?
How many people say smaller? Just curious. How many people say smaller? Couple. How many people say greater? How many people say the same? Okay, that's good. That's good. Yeah, that's good. At least you got. So you narrowed out one choice. The answer is greater. Here's the idea: is if you think of energy, energy is okay. So you have the energy of an unstretched spring, okay, and then you're going to add some. You're going to add some potential energy, right? By stretching the spring. Whoop, you stretch the spring. And so this, once you add it, becomes the energy of your stretched spring. So this is going to be bigger than this. Does that make sense? So the energy of the stretch, the total energy of the stretched system is going to be greater than the energy of the unstretched. So you would say that the rest mass of the stretched is greater than the unstretched.
only if it's moving like really fast, right?
Only if it's not moving. It's not moving. It's just a spring that's just... No, this doesn't have anything to do with motion anymore. This is the energy associated with mass just for being.
Okay.
And we
So
figured
it's
out this
micro-
notion of rest energy by considering relativistic effects. But this is true whether it's moving or not. Okay. All right, so the answer is greater. Okay, I'm going to stop the recording.